Hello students, welcome back to day 25 of PU2 Brahmastra Series. So now we are done with organic chemistry, inorganic chemistry, and today we are going to start with the first chapter of physical chemistry, and that is solutions. Okay, so in this lecture I have discussed almost 40 questions, and from this chapter you will be getting both numerical and theory questions. So theory questions I will be doing each and every question, numericals also I will be giving you all types of questions that is possible. So if you solve all the questions from this particular video, then definitely this chapter will be done for you. Okay, so now you need to sit with a notebook and a pen and note down all the questions, write down the answers and try to practice them. So let us start with the weightage of this chapter. So this chapter carries 12 marks in your PU board examinations. You will have 3 MCQs, okay, and 3 3-marker questions. Okay, so here you get 9 marks and here you get 3 marks, so total comes out to be 12. Now in this 3-marker questions, 3 3-marker questions, there will be 1 theory questions and 2 numerical questions. Okay, and trust me, these 2 numerical questions will be very easy, and these theory questions can be done from all the questions that I am giving you today. Okay, so let us start now. Okay, in today's lecture I'll be giving you 10 MCQs and almost 40 3-marker questions, including both numerical and theory questions. Okay, I think here it is 32 theory questions and 8 numerical questions. Okay, fine. Let us. Okay, now I want to announce something that is about PU2 Success Blueprint Test Series. So it is a test series for your PU2 to get 95% and above, launched by Diksha. And in this you will be getting 12 mock test papers, which includes 4 part tests and 8 full-length papers from the subject physics, chemistry, maths and bio or CS. Okay, and the first test will be released on 15th of December 2024. Okay, and in this you are not only getting the question papers, you will also be getting the video solutions with detailed explanation and one-shot revision videos, doubt clarification classes, and the question paper will be based on the latest syllabus and pattern. Okay, and all this you will be getting at a discounted price of only 599 rupees. So students, please do not delay, buy the test series as soon as possible, because the first test is starting from 15th of December, so that you can boost your preparation. Okay, fine. Now let us go back to our question. Question here is, which of the following statement is false? Okay, you should be very careful whether it is asked true or false, correct, incorrect. Okay, because that is where you do mistake. So now, the relative lowering of vapor pressure of a solution is equal to the mole fraction of the solute present in the solution. This is a correct statement. Next, passage of solute molecules towards the solution side through the semi-permeable membrane is called osmosis. No, osmosis is what? Passage of solvent molecules. Okay, so this is incorrect. So correct answer is option number B here. So what should be the correct statement? Passage of solvent molecules. Okay, next question number, okay. Now let us see the next question here. Which one of the following statements given below concerning the properties of the solutions describe a colligative property? So what is colligative property? Colligative properties are those properties of a solution or of a solvent, okay, of a solvent which changes on addition of, this is very important, on addition of a non-volatile solute. Okay, clear? Now if you see, vapor pressure of pure water decreases by the addition of nitric acid. So nitric acid is not a non-volatile solute, so we can exclude this option. Boiling point of water decreases by the addition of ethanol. So ethanol is also a volatile, so this is also not considered. Boiling point of pure benzene increases by the addition of toluene. Even toluene is a volatile, it's a volatile solute. So this also we can exclude. Next, vapor pressure of pure benzene decreases by the addition of naphthalene. Yes, this is correct because naphthalene is non-volatile. Okay. So when you add a non-volatile solute, the vapor pressure definitely decreases. The correct answer is option number D here. Okay. Next, question number 3. molar solubility of helium, nitrogen and oxygen are plotted against the partial pressure gas at constant temperature. Okay, so solubility with respect to partial pressure is given to you. Henry's law constant for these gases will lie in the following sequence. Okay, so what we can do is we can fix one constant pressure. Okay, so I'll take suppose this as the pressure. Okay, so at this pressure, what is the solubility? Solubility of oxygen is here, solubility of N2 is here, and solubility of helium is here. So I can say at any constant pressure, solubility of oxygen is more than nitrogen, is more than helium, right? So you know solubility and Henry's law constant are inversely proportional to each other. So what will be the order of Henry's law constant? O2, N2 and He. Okay, so we will get O2, N2 and He, option number B. Okay, next question number 4. Pi 1, Pi 2, Pi 3 and Pi 4 are the osmotic pressures of 5% W by V solution of urea, fructose, sucrose and KO respectively at a certain temperature. The correct order of their magnitude is, okay, so if you know pi value is equal to what? C into R into T, right? And C is what? Number of moles. Number of moles is what? Given mass, right? Given mass by molar mass. Okay, so I can say that the osmotic pressure is inversely proportional to molar mass. Okay, so whosoever, so this is C value, right? R into T, and volume is also there. So whosoever molar mass will be more, its pi value will be less, right? So now if I see, we have urea whose molar mass is 60. Okay, then we have fructose. Fructose molar mass is 180, and then we have sucrose, and sucrose molar mass is 342. Okay, next if you see here, last one is KO. Okay, but KO has an I value of 2. Okay, it dissociates to give you K plus and O2 minus. So here one I value will be multiplied. So when an ion dissociates, it will have more osmotic pressure. So definitely pi 4 has to be more. Okay, so we can eliminate these two options. Now coming to the next one, where the molar mass will be maximum, there the there it will be. So after C, so here the molar mass is minimum, 60 here is there, so pi 3 will be the highest value, sorry pi 1 will be the highest value, so after that pi 1 will come. Next you have 180, so after that pi 2 will come, and lastly pi 3 will come. So option number C is the correct answer here. Okay, so always remember, when an ion, or sorry, when a solute dissociates, okay, when a solute dissociates, the I value increases. Okay, next question number 5, the mixture which shows positive deviation from Raoult's law. So for showing positive deviation, what should happen? The A-B interactions should be weak. Okay, so now if you see chloroethane, bromoethane, ethanol and acetone, benzene, toluene, acetone and chloroform. So the correct answer for this question is option number B, because ethanol has very good hydrogen bonding, but when you put acetone in ethanol, the hydrogen bonding of ethanol is disrupted. Okay, so AB interactions are weaker here. Correct answer is ethanol and acetone. Next question number 6. Concentration terms like mass percentage, ppm, mole fraction and molality do not depend on temperature. However, molarity is a function of temperature because volume depends on temperature and molarity involves volume. Correct answer is option number A. So if you remember, molarity formula is number of moles by volume into 1000. So if temperature increases, volume increases, molarity will decrease. Okay. Next, so here is an assertion reason question. Molecular mass of benzoic acid is determined by colligative property is found high. The reason dimerization of benzoic acid in the solution. Yes, so this is correct. See, benzoic acid undergoes dimerization in the solution. So whatever molecular mass you find out, that becomes more than the actual value. Okay, so that is why the both assertion and reason is true, and reason is the explanation. Option number A is the correct answer. So here you should remember, if a solute, okay, undergoes dissociation, then the molecular mass calculated will have less value. Okay, and if a solute undergoes association, then the molecular mass calculated will have higher value. Clear? Okay. Next, question number 8, the mole fraction of the solvent is 0.9. The relative lowering of vapor pressure is, okay. So if you remember, mole fraction, relative lowering of vapor pressure, that is delta P by P naught is equal to X of the solute. Okay, so if mole fraction of the solvent is 0.9, then mole fraction of solute will be 0.1 and relative lowering of vapor pressure will be 0.1. So option number A is the correct answer here. Next, dissolution of calcium chloride in water is an exothermic process, while that of ammonium nitrate is an endothermic process. The observation is, okay, solubility of calcium chloride decreases with the increase in temperature, and that of ammonium nitrate increases with the increase in temperature. Next one, solubility of both decrease with the increase in temperature. No. See, if it is an exothermic, okay, if temperature increases, solubility will, exothermic, temperature increases, solubility will decrease. Endothermic, temperature increases, solubility increases, right? So the first one, dissolution of calcium chloride in water is an exothermic process, while that of an ammonium nitrate is endothermic process. The observation is, so solubility of calcium chloride, if it is an exothermic process, so when you increase the temperature, it will decrease. So this part is correct. And that of ammonium nitrate increases with the increase in temperature, that is also correct. So option number A is the correct answer here. Next, question number 10. When acetone and chloroform are mixed together, which of the following observation is correct? Okay, so when you have chloroform and acetone, okay, chloroform is Cl, Cl and Cl, and we have acetone like this. Okay, so one second, this will be C, right? So now there is an hydrogen bonding here. Okay, so the AB interactions increases. This is suppose A and this is B. Okay, AB interaction increases and they show negative deviation. Okay, so here AA and BB interactions are stronger than AB interactions. No, AB interactions are stronger. AA and BB interactions are weaker than AB interactions. Yes, this is correct. Option number B is the correct answer here. Okay, fine. Now let us move towards the 3-marker questions. So I'll be discussing all the theory questions first, then I'll be giving you numerical questions. Okay, so let us solve them. What is molarity? How does it vary with temperature? Write its SI unit. So I hope all of you can answer this. So what is molarity? Molarity is, okay, defined as the number of moles of solute per unit volume of solvent. Okay, is denoted by capital M. Now if I want to write molarity, okay, molarity is equal to number of moles by volume in ml into 1000. Okay, so number of moles will be, I can write given mass by molar mass into 1000 by volume of the solution, right? Sorry, here I'll put volume of the solution. Okay, and this one should be in ml. Now how does it vary with temperature? So now if you increase the volume, okay, sorry, if you increase the temperature, volume will increase and molarity will decrease. So here you can write down when temperature increases, volume increases, molarity decreases. Okay. Next, write its SI unit. So SI unit of molarity is, okay, molarity SI unit. Okay, so it is I can write down like number of moles, okay, per liter. Okay, moles per liter. Or if I want to write in terms of I can write this moles. Yeah, you have to write in terms of moles per liter, or capital M is the denotation. Okay, clear this question? Next, question number 2. Mention the factors on which the solubility depends. So you should know 3 factors: nature of the solute, nature of the solvent, pressure and temperature. Okay, this can be a very important question. Okay, next, question number 3. Sugar is soluble in water and not in benzene. Give reason. What is crystallization? What is dissolution? Okay, so here sugar can form hydrogen bond with water. Okay, that is why it is soluble in water. Next, what is crystallization? So when you are dissolving any solid, okay, when you dissolve more than the amount possible, after that what happens? When you add the extra amount, it collapses and some particles come out of the solvent. That is called as dissolution. Okay, sorry, crystallization. So when some solute is added in the solvent, some solute dissolves and its concentration increases in the solution. That is called as dissolution. Sorry, this is dissolution. Okay. Next, some solute particles in the solution collides with other solid particles and separates out from the solution, and this is called as crystallization. Clear? Next question. What is saturated solution? What is unsaturated solution? What is the effect of temperature on solubility of solids in liquids? Okay, so saturated solution means when you cannot add any further solute to a solution. Unsaturated means when you can add further solute, when you can dissolve further solute in a solution. And effect of temperature on the solubility, it depends on the whether the dissolution is endothermic or exothermic. Okay, so saturated solution means no more solute can be dissolved. Unsaturated solution means some more solute can be dissolved at the same temperature. Okay, and if it is endothermic, then increasing the temperature, the solubility will increase if you increase the temperature, and if it is exothermic, the solubility will decrease on increasing the temperature. Okay, next, question number 5. What is the effect of the pressure on the solubility of solid in a liquid, and what is the effect of temperature on the solubility of gas in a liquid? Give reason. Okay, so first of all, pressure has no effect on the solubility of solid in a liquid. And talking about gas, as the temperature increases, the solubility of the gas in liquid decreases because it is an exothermic process. Okay, so remember, solubility of gas, okay, in liquid, solubility of gas in a liquid is exothermic. Okay, and if it is exothermic, then what will happen? If temperature increases, solubility decreases. Okay, clear? Okay, next question. State Henry's law and write its mathematical formula. What is the significance of Kh? So this is also very, very important definition. Okay, very important definition, this one. So you can write down, Henry's law states that at constant temperature, the solubility of a gas in a liquid, okay, the gas amount of gas that is dissolving in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. Now its mathematical formula is P is equal to Kh into X, where X is what? So you have to explain all the term here. Okay, I'll explain what is P. P is the partial pressure of gas. Okay, Kh is Henry's constant. Okay, and X gas is the mole fraction. Clear? So what is the statement saying? That if the temperature is constant, now x, the solubility is x represents the solubility. Okay. So the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the liquid. Okay. Next, what is the significance of Kh? So if you see in this expression, I can write Kh is equal to P of the gas by mole fraction of the gas, or I can say solubility of the gas, right? So I can say that solubility of the gas is inversely proportional to Kh. If Kh is more, solubility will be less. If Kh is less, solubility will be more. Okay. So that is why higher the Kh value, less is the solubility. Okay. Next, at a given temperature and pressure, N2 is more soluble than He in water, whose Kh value is more. So definitely, if N2 is more soluble than He is less soluble, then its Kh value should be more. Okay. Next, aquatic species are more comfortable in cold water than in hot water. Why? Okay. So you can see the first one, solubility order is what? Solubility N2 is more than helium, right? Then what will be for this one? If I talk about Kh value of N2 is less than helium. Okay. Next, aquatic species are more comfortable in cold water than in hot water. Why? So here also you can answer like this, that in cold water, so what we discussed just now, that solubility of a gas, okay, in liquid is exothermic. That means if the temperature is less, more will be the solubility. So in cold water, what happens? More amount of oxygen is dissolved in water, but in hot water, less amount of oxygen will be dissolved, right? So that is why in cold water more oxygen is dissolved. So aquatic animals are more comfortable in cold water because they will get more oxygen here. Okay. Next, give 3 applications of Henry's law. This is direct question. So first is, it is used in carbonated beverages. Second, it is used by scuba divers, and third, it is used by mountain climbers for respiration at high altitudes. As the pressure decreases, solubility of O2 in the blood decreases, causing anoxia. Okay. Next question, explain the cause of bends in scuba diver and how is it controlled. So first let us understand this one. So you should know one thing, if pressure increases, solubility will increase, right? Now let us understand, suppose you are here we have water, okay, sea, and even scuba diver is here. So scuba diver now has more pressure, right? So that means more amount of gas will dissolve in his blood, right? So that is why what happens, the amount of N2 that is dissolved in this person will be more. Okay. Now when the person comes out, pressure is decreasing, pressure is proportional to height. Okay. Depth, if the height is more, pressure is more. Now when the person comes up, okay, here the height is less, pressure is less, so solubility will be less. So whatever N2 got dissolved in the blood will come out in the form of bubbles. Okay, and these bubbles can block the capillaries and blood veins, and which causes like severe pain for the scuba diver. So that is why this is recommended. Let these oxygen cylinders of the scuba divers are mixed with helium gas. Okay, and helium gas has very less solubility, so it doesn't dissolve more, right? So when the person comes out also, there is no much problem. So you can see here, okay, see, as scuba divers go down in the sea, okay, pressure increases underwater. Increased pressure increases the solubility of nitrogen in the blood. When the diver comes to the surface, the pressure gradually decreases, and this releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. Now this blocks the capillaries and create a medical condition called as bends, which is painful and dangerous to the life. Okay. So next is how is this controlled? Okay, how this problem can be solved. So for solving this, the tanks used by the scuba divers are filled with helium. Okay, 11.7% of helium is there, nitrogen 56.2% and oxygen 32%. Okay, Because of the low solubility of helium in the blood than nitrogen. Okay, so helium is less soluble there, so helium doesn't get dissolved in the blood of the scuba divers, and it protects them from this dangerous situation. Okay, next question number 10 is very important, like Henry's law. This is also important. State Raoult's law and gives its mathematical formula. What is vapor pressure? Vapor pressure of CHCl3 and CHCl2 are 200 and 415 mm of Hg, which is more volatile. Okay, so first let us see Raoult's law. Raoult's law states that in a solution of two volatile liquids, suppose we have mixture and there are two volatile liquids. Volatile liquids means both can evaporate. Okay, two volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction. Okay, so for example, what I want to say, you see, suppose here you have a container. Okay, you have A and B and both are volatile, means both can produce vapor. Okay, both can produce vapor. Now how much vapor of A will be produced will be proportional to the mole fraction of A. Similarly, how much vapor pressure of B will be produced will be proportional to the mole fraction of B. Okay, so mathematically how it is written, I'll add here, mathematically for PA is proportional to XA. Okay, the partial pressure of the component A is proportional to its mole fraction. Okay, next, what is vapor pressure? So the pressure exerted on the liquid by the vapor present above the liquid surface when they are in equilibrium with the liquid is called as vapor pressure. Now see, what happens here is, in this container there are two processes happening together. Okay, one is A and B evaporating, so evaporation. Okay, one is evaporation and another is condensation. Okay, so when these two processes happens together, means one molecule is going to the vapor phase, another molecule is coming to the liquid phase. When these two processes are at equilibrium with each other, at that time whatever vapor is present here, they exert a pressure on this liquid surface. Okay, and this pressure exerted by the vapor on the liquid when the system is at equilibrium is called as vapor pressure. Okay, now next question is again very interesting one, that is CHCl2, both vapor pressure are given, right? So CHCl3 and CHCl2. CHCl3 vapor pressure is 200 and CHCl2 vapor pressure is 415, right? So what does it mean? That in CHCl2, okay, more amount of vapor has formed there, right? In this, like if I see the container, CHCl2 vapor is more here, right? That means what? It is more volatile, it can easily escape to the vapor phase, so that is why more number of vapors are present, so vapor pressure is also more, that is why, right? So I can say which is more volatile, obviously it is CH2Cl2. Okay, next is question number 11. Why the vapor pressure of the solvent decreases on addition of a non-volatile solute? Now let us first understand this, then I will show you the answer. So now you see, suppose this is a container. Okay, this is the lid for that container and here you have water particles. Okay, now these surface molecules are water molecules, right? Now these were evaporating and because of that there is some vapor produced here and this vapor creates a vapor pressure. But now suppose you add a non-volatile solute. Okay, non-volatile solute means the solute which cannot form vapors. Okay, so suppose here we have, this is the level. Okay, now earlier what happened, when there was no solute, all the particles that were present were of the solvent. But now once you added the solute, so this is solvent particles. Okay, but there are some solute particles also present now. Okay, the surface is not only of the solvent, now the surface contains some solute particles also. Now what was the before case when there was no solute? One second. Yeah, when there was no solute, what happened? All these particles were solvent molecules, right? So now you see in this case there were 5 particles which can go to the vapor phase, but now here you can see only 3 particles can go to the vapor phase. Why will these not go? Because these are non-volatile, right? It is given non-volatile solute is added. Non-volatile means which cannot evaporate, right? So here we will get vapor of 3 and here we will get vapor of 5. So definitely vapor pressure here will be more. When you add a non-volatile solute, the vapor pressure will definitely decrease, right? So that is the reason you can see here. Okay, in a pure liquid, the entire surface is occupied by the molecules of the liquid. If a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. Okay, the solute is non-volatile, so whatever the vapor pressure will be created of the solution after adding solute, that is also due to the addition or due to the presence of solvent molecules only, right? Now in this solution, the surface has both solute and solvent molecules, thereby the fraction of the surface covered by the solvent molecules get reduced. Right, earlier suppose full surface was covered with solvent molecules, now some of the parts will be covered by the solute molecules. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced, thus the vapor pressure is also reduced. Okay, now let us see the next question. What is ideal solution? Give example. Draw the graph of vapor pressure against mole fraction for ideal solution. Okay, so first we have to write what is an ideal solution. Okay, one second. Yeah, so ideal solution is a type of solution which obeys Raoult's law. Okay, here a question may be asked, what do you mean by it obeys Raoult's law? So I want to explain you that. I haven't added that question. So now see, when the vapor pressure, okay, when the vapor pressure of the ideal solution, okay, is equal to the calculated value, is equal to the calculated value from the Raoult's law. Okay, when the vapor pressure of the ideal solution is equal to the calculated value from the Raoult's law is called as ideal solution. Okay, means using Raoult's law you calculated some vapor pressure and you observed, you did the experiment and you calculated the vapor pressure. If both are coming equal, then it is called it obeys Raoult's law. Okay, now these examples are very important, so you can remember the structures. If they are similar, their vapor pressure will be same, right? For example, benzene and toluene, bromoethane and chloroethane. Okay, then you have N-hexane and N-heptane. Okay, next coming to draw the graph of the vapor pressure against the mole fraction. So if you want to draw the graph, you can see here, this is the graph of pressure, okay, versus mole fraction. So this is for one component, this is for another component, and this is the total pressure. Clear? Okay. Next, coming to question number 13, what is non-ideal solution? Give example. So if you have remembered what is an ideal solution, non-ideal solution, you can answer very easily, right? So a solution which does not obey Raoult's law is a non-ideal solution. Example here also very important, HCl and water, ethyl alcohol and water, ethyl alcohol and acetone, CS2 and acetone. Okay, so you can remember two examples as ethyl alcohol common and acetone is common in two examples. Okay, next, draw the graph of vapor pressure against mole fraction for non-ideal solution. Now non-ideal solutions are of two types, right? Positive deviation and negative deviation. So if it hasn't asked you for which deviation, you need to draw both of them. So this is for positive deviation and this is for negative deviation graph. Okay, graphs are very important in this chapter. Next, give the difference between ideal solution and non-ideal solution. Just 3 points you should remember. First, definition obeys Raoult's law, does not obey Raoult's law. Delta H mix is equal to 0, delta H mix is not equal to 0. Okay, delta V mix equal to 0, delta V mix is not equal to 0. Now AB interactions are equal to AA and BB interactions. AB interactions are not equal to AA and BB interactions. Okay, next is question number 14. differentiate between the types of non-ideal solution. So positive deviation and negative deviation. Okay, so AB interactions are weaker than the AA and BB interactions, that is called positive deviation. Now if AB interactions are stronger than AA and BB interactions, that is a negative deviation. Okay, next, P total is greater than P1 x1 plus P2 x2 and P total is less than P1 x1 plus P2 x2. Delta H mix is positive and here delta H mix is negative. Okay, next, in positive deviations, sorry, this point is not there. Next, example of positive deviation, ethanol and acetone, CS2 and acetone. This is very important. Questions can be asked from here. Next, phenol and aniline and chloroform and acetone are the examples of negative deviation. Okay, so in negative deviation, what happens? Interactions increases. Positive deviation, interaction increases. Okay, sorry, positive deviation, interaction decreases. Okay, is weaker and here it is stronger. Okay, next, give the type of deviations with reason. So just now we have learned the example, so we can answer this question. Acetone and ethanol, this is your positive deviation. Why? Because in ethanol there is strong hydrogen bonding, but when you put acetone in that, the hydrogen bonding is disrupted. Okay, the interactions become weaker. That is why it is a positive deviation. So you can see here, in pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the ethanol molecules and break the hydrogen bonds between them. Now, due to the weakening of interactions, the solution shows positive deviation from the Raoult's law. Next, you have phenol and aniline. Okay, phenol and aniline will have strong hydrogen bonding, so they will show negative deviation. Okay, this is because the intermolecular hydrogen bonding between the phenolic proton and the lone pair on the nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between the similar molecules. Okay, so the hydrogen bonding between the phenol molecules and the aniline molecules and the hydrogen bonding between phenol and aniline. Okay, so aniline and phenol hydrogen bonding is much more stronger than the hydrogen bonding between phenol and aniline itself, right? So that is why this is a negative deviation. Next, you have chloroform and acetone. So this is also negative. Okay, that is because of chloroform molecule can form hydrogen bond with acetone molecule. Okay, so you can show this bonding also like this. So chloroform is like this, and we have here hydrogen bonding is present between this one. Okay, clear? So let us see the next question here. What are azeotropes? Give example. Mention the types of azeotropes. Okay, so for azeotrope, first you should know some basic points of definition. Okay, I want to write in point wise so that you can remember. It has same composition, okay, in liquid and vapor phase. First thing. Okay, second point is it has same boiling point. Okay, means suppose you are mixing two liquids A and B. Okay, after mixing, A and B will boil at the same boiling temperature. Next one is they cannot be separated by fractional distillation. Clear? Fine. Now coming to example, binary liquid mixtures having the same composition in liquid and vapor phase and boil at a constant temperature is called as azeotropic mixture. Example, 95% ethyl alcohol and 5% water. Okay. Now what are the types? We have two types. One is maximum and another one is minimum boiling azeotrope. Okay. Now coming to differentiate between maximum and minimum boiling azeotrope. So here you remember, maximum boiling azeotrope means the boiling point is more than the boiling point of both the solutions. Okay. Now if the boiling point has increased, that means the particles must be very tightly attracted towards each other. That is why we need to give them more temperature to boil them. So if the particles or if the two solutions A and B are very tightly attracted, then that is negative deviation. Okay. Similarly, minimum boiling azeotrope means they will boil at a very lower boiling point. So that means the interactions is weak. If the interactions are weak, then it is positive deviation. Okay. Next we have they boil at a temperature higher than the boiling point of each component, and here they boil at a temperature lower than the boiling point of each component. Okay, now example here nitric acid and water, where nitric acid should be 68% and water should be 32%. Okay, and example here is ethanol and water, where ethanol is 95% and water is 5%. Okay, clear? Fine. Next is colligative properties. This is very important. From here most of the numericals are being asked. So what do you mean by colligative properties, and name them? So the properties of the solution which depends on the number of solute particles and not on their nature is called as colligative properties. Okay, depends on the number of the particles and not on their nature. Next is your what are the colligative properties? We have relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay, these are the 4 colligative properties that you should know. Okay, next is what when does liquid boil, what is ebullioscopic constant, and what is its SI unit. Okay, so when does liquid will boil? So liquid boils at the temperature when the vapor pressure of the liquid is equal to the atmospheric pressure. Okay, so if you see, now see, suppose we have a liquid. Okay, it will have some vapor pressure. Now if this vapor pressure is equal to the atmospheric pressure, at that time the liquid will start to boil, right? Now similarly, if you go at a higher altitude, right, if you see at higher altitude the atmospheric pressure is very less, right? So it is at a very quick time the vapor pressure of the liquid matches the atmospheric pressure. So that is why what happens at higher altitude the boiling point decreases. Okay, because they will easily match the atmospheric pressure, because at higher altitude the atmospheric pressure is less. Okay, next, what is ebullioscopic constant? So if you have known the formula of delta TB is equal to Kb into m, right? So Kb will be equal to delta TB by m, right? So Kb is nothing but your ebullioscopic constant. Okay, so now how will you define it? So ebullioscopic constant is that when you have delta TB is equal to 1 Kelvin and molality is equal to 1 mole. Okay, so it is the increase in boiling point produced when 1 mole of a non-volatile solute is dissolved in a pure solvent. Okay, when 1 mole of a solute is dissolved in 1 kg of solvent, whatever is the delta TB found, that is your Kb. Okay, now if you talk about the unit, so delta TB value is Kelvin, moles is kilogram mole inverse, sorry, kilogram kg inverse, right? We have moles per kg. Okay, so we'll get Kelvin mole inverse kg. Okay, next, give the relation to calculate Kb using the enthalpy of vaporization. Draw the graph of vapor pressure with temperature to show the elevation in boiling point. Which one has higher boiling point? Okay, so first, if you see, this formula is rarely asked in the exam, but you should be remembering that. So Kb is equal to Rma delta Tb square in divided by 1000 into delta H vaporization. Okay, so what are the terms here? R is your gas constant. Okay, Ma is the mass of solvent. Okay, Tb is the boiling point of the solvent. Delta H vaporization, okay, is the enthalpy of vaporization. Clear? Done? Next, draw the graph of vapor pressure with temperature to show the elevation in boiling point. So vapor pressure with temperature, so you have solvent, you have solution, and then you can draw this graph. So you can see that at this vapor pressure, okay, at this particular pressure, what are the temperatures? You have T0B and you have TB, right? So I am seeing here, you see, for the solvent that at a pressure of 1 atm, for the solvent the I can say at this pressure the solvent, the value was T0B, but when it became a solution, when you added some solute to it, it is boiling at TB, right? So this is your delta TB, and this is equal to your delta TB is equal to Kb into m, okay, the elevation in boiling point, Kb into m. Next, which one has higher boiling point, 0.01 m NaCl or 0.01 m Na2SO4? So here if you see, for electrolyte solution we have I into Kb into m. For NaCl we have 2 ions, so I value is 2 here, and here the I value is 3. So if I value is more, delta Tb value will be more. So definitely it is Na2SO4. Okay. Next, when does liquid freeze? What is cryoscopic constant and what is its SI unit? So similar question. So liquid will freeze when the vapor pressure of the liquid is equal to the vapor pressure of the solid. Okay. Next, what is cryoscopic constant? It is the decrease in the freezing point produced when 1 mole of a non-volatile solute is dissolved in 1 kg of pure solvent. Okay. Next, what is its SI unit? The same, Kelvin, kilogram, mole inverse. Okay. Next is question number 23. Give the relation to calculate the Kf using the enthalpy of fusion. Okay, so we have this formula, Kf is equal to Rma square Tf square divided by 1000 into delta H of fusion. Next, draw the graph of vapor pressure with temperature to show the depression in freezing point. Okay, so you can see here we have vapor pressure, we have temperature. Okay, so now this was the freezing point when we have only solvent, right? This is T naught F. Now for the solution, the vapor pressure, the freezing point is Tf. So T naught F minus Tf is your delta Tf, which is equal to Kf into m. Now give reason. To clear the snow covered road and hill, salt is added. So that is very simple here. So when you sprinkle the salt on the snow, okay, covered roads and hilly areas, the snow starts to melt. Why? Because of the depression in freezing point. Okay, so when you add salt, the freezing point decreases. So now in that particular temperature, it cannot be in the freezing state, it starts to melt. Okay, so it's as a result formation of water take place, which helps to clear the road. Clear? Next, what is osmosis? Give an example. What is semi-permeable membrane? Give example for natural and artificial semi-permeable membrane. Okay, so osmosis is the flow of the solvent from lower concentrated solution to higher concentrated solution. Okay. Next, membrane which allows only the solvent to pass through it is called as semi-permeable membrane. Examples of natural membrane are pig's bladder and parchment membrane, and for synthetic it is cellophane papers. Okay. Next, give reason for the following. Raw mango shrivel when picked in brine solution, that is salt plus water solution. Blood cells collapse when suspended in saline water. Wilted flowers revive when placed in fresh water. Okay, so first of all, raw mango shrivel means shrink. Okay, when you keep them in solution. So if you see here, you have a raw mango, okay, and you have salt solution here. So inside mango, what? There is more water, okay, and outside there is salt. So this is a low concentration solution and this is a high concentration solution. So what will happen? Water will flow out from the mango to the solution and it will cause the mango to shrivel. Okay, so that is because this is because of moving out of water, or we call it exosmosis. Okay, so that is because of exosmosis, water molecules of the mango enters into the brine solution. Okay, next we have blood cells. Okay, blood cells collapse when suspended in saline water. The same thing, blood cells will have some water content, outside the concentration is more. So from low concentration to high concentration, water will flow and the blood cells will collapse again, right? So that is also because of exosmosis. So here I want to tell you what is exosmosis and endosmosis. See here, exosmosis means water flowing out. Okay, endosmosis means water flowing in. Okay, Next, wilted flowers revive when placed in fresh water. So there is a, suppose a flowers are there and it is like wilted, or it is like it has lost its that firmness. Okay, when you put it in water, that has already lost its water, right? And outside water this concentration is more, right? So from there it will flow inside the flowers, and that is called as endosmosis. Okay, so endosmosis, water molecules enter into the flowers. Clear? Next, explain isotonic solution with example hypertonic solution and hypotonic solution. So before going to this question, I want to do another question, then we'll come back to this solution, this question. Yeah, first, what is osmotic pressure? Give example, give equation, and what is reverse osmosis. Okay, so here just first I want to explain you with the diagram. Okay, so suppose we have a membrane here, okay, and we have solution here and we have solvent here, right? So what will happen? This is having more solvent, this is having less solvent, so water will flow like this, osmosis. Okay, so now what you can do is you can put a pressure on this side. Okay, just you have to put a pressure so that these water molecules cannot flow from solvent to solution side. Or I can just write, like, let me write down in this way. Okay, so this is low concentrated and this is high concentrated solution. Okay, sorry, one second. This is high concentrated solution and this is low concentrated solution. So from here water will flow. So if you apply a pressure on this side just to stop the flow of the solvent molecules, that is called as osmosis, or that pressure that you required to stop osmosis is called as osmotic pressure. Okay, equation we will write. Now what is reverse osmosis? See, water was flowing from this side, right? You gave some pressure, it stopped. But if you give more pressure, what will happen? Water from this side will flow to this side. Okay, water will start flowing from this side to this side, right? So now what will happen when water will flow from this side? So when I am saying high concentration, it is high concentration of the solute. Okay, and here it is low concentration of the solute, right? So just if you want to see the definition of osmosis once again, let me show you. Yeah, so you can see what is osmosis: the flow of the solvent molecules from the lower concentrated solution to the higher concentrated solution, right? So that is what we have drawn here. Yeah, so this is the flow of the solvent molecules from the low concentrated solution to the high concentrated solution. It was flowing like this. You put a pressure to stop it. That pressure is called as osmotic pressure. Now if you give more pressure, suppose you gave 5 units of pressure and you stopped it. If you give 6 units of pressure, what will happen? It will flow in the opposite direction. That is called as reverse osmosis. Okay, so now we will see the definition here. The external pressure applied on the concentrated solution to stop osmosis is called as osmotic pressure. What is its mathematical equation? It is pi is equal to C into R into T, where C is what? Concentration. Okay, and concentration is given in terms of molarity. R is gas constant. Okay, and T is temperature. Clear? What is the value of R? 0.0821 liter atm mole inverse, Kelvin inverse. Okay, fine. Now let us go back to this question, that is, what is isotonic solution? With an example you have to explain. So now we understood what is osmotic pressure, right? So if two solutions are there, A and B, and if they have the same osmotic pressure, then it is called isotonic solution. Example, RBC is isotonic with 0.9% NaCl solution, which is called normal saline. Okay, so what is the pressure of RBC? It is equal to 0.9% NaCl solution. Now it is used in injections instead of distilled water. Okay, next, what is hypertonic solution? Clear? So the solution whose osmotic pressure is higher than that of the given solution. Suppose you have one solution A, another solution B. One solution A has a pressure of 5, another has more than 5, then that is called as hypertonic solution. Hypotonic, so example you can see here, when RBC is placed in sea water. Okay, the sea water concentration is definitely not 0.9, it is more than 0.9, so that means the pressure will be more. So when RBC is placed in seawater, water passes out of the cell due to the osmosis and the cell shrinks. Okay. Next, what is hypotonic? The solution whose osmotic pressure is higher than that of the solution whose osmotic pressure is lower, okay, then that of the given solution is called as the hypotonic solution. Okay, so this is about hypotonic solution. When RBC is placed in a hypotonic solution, they swell and even burst. Okay, so if you keep this one, so this is RBC, okay, and we know its pressure is equal to 0.9. Now if I kept a solution of 0.5, right, now what will happen? The water will flow inside this and it will swell and burst. Okay. Next, what is edema? What is the cause for the movement of water from soil to plants? Preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Explained. So this is all about osmosis. So what is edema first? It is a medical condition. Okay, people taking a lot of salt or salty food experience water retention in the tissue cells. So when you take a lot of salt, right, what happens then? Your tissue has less cell, right? So that is why water will flow inside the tissue. So tissue now contains more amount of water. Okay, and the intracellular spaces, because of osmosis, this results in puffiness or swelling called as edema. Okay, when you take lot of salty food, okay, your tissue has like more salt content. Okay, it's a concentrated solution. So water from the environment like from the neighborhood enters into the tissue, which is called as edema. Okay. Next, what is the cause for the movement of water from soil to plants? It is osmosis. Okay. Next, preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Okay. Now when you put salt on the meat, okay, what if any bacteria is there, they will lose their water. Okay, once they lose their water, they will die. So that is what, through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. Okay, the bacteria will lose water because outside it is high concentration, right? So the water of the bacteria will flow out and it will become dead. Okay. Next is we have a question here. Okay, this I have already explained. Next, explain the desalination of water by reverse osmosis. Name the semi-permeable membrane used in this process. Okay, so what is the application of reverse osmosis? It is used in desalination of water. So you can see that here, reverse osmosis is used in desalination of seawater when the pressure more than the osmotic pressure, that is 30 atm at 25 degrees Celsius, is applied to the seawater. Pure water is squeezed out of the seawater through the semi-permeable membrane. What type of semi-permeable membrane is used? That is cellulose acetate. Okay, so now you can see here one thing. You have suppose fresh water and you have salty water, right? So now what happens? In this fresh water and salty water, if you see, in the salt water, the osmosis will be in this way, right? Normal osmosis. If you give osmotic pressure, it will stop. But if you give pressure more than pi, then what will happen? Water will flow from here. The pure water from here will start flowing towards the fresh water. Okay. Next question. Why osmotic pressure is used to calculate the molecular mass of the polymers, and what will happen to the RBC if it is placed in 1% NaCl and 0.5% NaCl solution. Okay, so now you see this method is used. First of all, why osmotic pressure is used? Because this method uses molarities instead of molalities. All other uses molality, right? Here osmotic pressure is the only thing where we use molarity. So that is why that is considered to calculate the molecular mass of the polymers. Next, what will happen if you keep it in RBC 1% NaCl? Okay, you know RBC is 0.9%, right? And if outside we have 1%, right? So that means what? Water will flow inside here, right? Because, sorry, one second. Okay, 1 second. 1% NaCl, right? That means this is high concentrated, okay? And this is low concentrated. right? So solvent molecules move from low concentrated solution to high concentrated solution. So water will move out and it will shrink, right? So that is why can be measured at room okay, you have to give first 2 points here. So first is it is using molarity, and second thing, it can be used to measure even at room temperature. Okay. Next, if you see at 1% RBC, what will happen? The RBC will shrink because water will go out. Now the second case arises here is, if you have, this is 0.9% and here we have like 0.5%. Okay. Now 0.5% here, that means this is more concentrated and this is less concentrated. So solution will move here, water will move inside. Okay, if water moves inside, then what will happen? It will allow it to swell. Okay, so that is why the above phenomenon is called because RBC is isotonic with 0.1 NaCl solution, because at 0.91 it is isotonic, with 0.5 water will flow inside. Okay. Next, what is abnormal molar mass? What is Vant Hoff factor? What is the conclusion drawn when the Vant Hoff factor of a solution? Okay. So first, what is abnormal molar mass? The molar mass determined by the colligative properties is sometimes found to be lower or higher than the expected normal molecular mass, and this is called as abnormal molecular mass. Next, what is Vant Hoff factor? Vant Hoff factor is the ratio of normal mass to abnormal mass. Here are the three formulas of Vant Hoff factor. Normal mass by abnormal molar mass, observed colligative property by calculated colligative property, number of particles after dissociation divided by number of particles before dissociation. Okay. Next, we have done here. Okay. What is the significance of Vant Hoff factor? This is I. Okay. And give the relation between the degree of association and I and the degree of association and I, right? So if I is equal to 1, solute does not associate or dissociate. If I is greater than 1, solute will dissociate. If I is less than 1, solute will associate. Okay. Next, we have for dissociation, alpha is equal to I minus 1 by n minus 1, and for association it is alpha is equal to I minus 1 by n minus 1. Here n is what? Here n is number of particles. Okay, fine. Now we are going to solve numerical questions. Okay, I'll be telling you the formulas and all. We'll solve the questions here. Now 450 centimeter cube. So here you should remember 1 centimeter cube is equal to 1 ml. Okay, so I can say 450 ml of an aqueous solution of protein contains 1 gram of protein. The osmotic pressure of such a solution at 310 Kelvin is found to be 3.1 into 10 to the power of minus 4 bar. Calculate the molar mass of the protein. So first I will note down all the values that is given to me. First I can write volume is 450 ml. Okay, and mass of the protein means W2 is 1 gram. Okay. Then osmotic pressure at 310 Kelvin. So temperature is 310 Kelvin. Osmotic pressure is how much? 3.1 into 10 to the power of minus 4 bar. Okay. Then you have to calculate the molar mass. R value is also given. So if I have pi is equal to C into R into T. Pi is equal to W2 by M2 into 1000. Okay, by volume in ml, okay, into R into T. So now if I want to calculate here, okay, what is, I want to calculate M2, right? So I will calculate M2, that will be equal to pi will come here, right? Pi will come here, M2 will come here. So W2 is 1 gram, okay, pi value is 3.1 into 10 to the power of minus 4 bar, okay. Then I have 1000 here, and volume is 450 ml, and then you have R is 0.083, okay, and temperature is 310 Kelvin. Okay, So if you see here, if you solve all this, you will be getting around 1844444 gram per mole. Okay, just do the calculation, you will see this. Okay. Next, question number 2. So 1 gram of a non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.4 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kilogram mole inverse. The molar mass of the solute is. The same formula again we will use for freezing point depression, that is delta TF is equal to Kf into M. Okay, but Kf molality will be W2 by M2 into 1000, okay, by volume, sorry, by W1. Okay, next Kf value is 5.12. Okay, next W2 value is 1 gram. Okay, next I want to write M2, I have to find out, right, 1000. What is the mass of the solvent? 50 gram. Okay, and what is the Kf value? Kf value is 0.4 Kelvin. So if I solve this and calculate, M2 value will be 256 gram per mole. You can check the calculation and see whether you are getting this answer or not. Next, question number 3. On dissolving 3.46 gram of a non-volatile solute in 100 gram of water. Okay, so I will note down the values again. So W2 is 3.46 gram. Water mass, that is W1 is 100 gram. Okay, the boiling point of the solution was raised to that of the pure water by 0.12 Kelvin. So delta TB is equal to 0.12 Kelvin. Calculate the molar mass of non-volatile solute, and Kb value is 0.51. Okay, and we need to find what? Molar mass of the solute. So same we will use here, delta TB is equal to Kb into M. Okay, so now if I use delta TB value is 0.12. Okay, let me write down the formula of M also, then we will substitute. Okay, delta TB is equal to Kb, okay, into M, W2 by M2 into 1000, okay, by W1. So now if I substitute these values, that will be delta TB will be equal to 0.12, okay, Kb value is 0.51, okay, so W2 is 3.46 and M2 value is, we have to find out, into 1000, okay, W1 is 100. Fine. Now if I solve this, M2 value that is going to be calculated will be 147.05 gram per mole. Okay. Next, question number 4. 31 gram of an unknown molecular material is dissolved in 500 gram of water. The same thing, first we will write down W2 is 31 gram, okay, then W1 is 500 gram, okay. The resulting solution freezes at 271.4. So TF is 271.14 Kelvin. Next, calculate the molar mass of the material. You have to calculate the molar mass. Given Kf for water is 1.86 Kelvin kilogram mole inverse. Okay. Then T naught F value is already given to you, 273 Kelvin. Okay. We need to calculate again the molar mass. So it's the same formula, I will write here directly. Delta TF is equal to what? TF minus T naught F minus TF is equal to KF into molality, that is W2 by M2 into 1000 by W1. Okay. So now if I solve this one, what is delta T naught F? T naught F is 273. Okay. Minus TF is 271.14. Okay. KF value is how much? 1.86. Okay. Molality, W2 is 31. Okay. Then I have M2. M2 I have to find out. Okay. Into 1000 okay, by W1 is 500. Fine, you have to solve this and calculate M2, you will be getting around 62 gram per mole. I want all of you to do this calculation by your own and check the answer, okay. Next question number 5, vapor pressure of benzene is 200 mm of Hg. When 2 gram of a non-volatile solute is dissolved in 78 gram of benzene, benzene has a vapor pressure of 195 mm of Hg. Calculate the molar mass of the solute. Molar mass of the benzene is 78 gram per mole. Okay, so let us note down the values first. Okay, you have the vapor pressure of benzene, means P naught value is 200 mm of Hg. Okay, now when 2 gram of a non-volatile solute, means W2 is 2 gram, okay, is dissolved in 78 gram of benzene, W1 is 78 gram. The benzene has a vapor pressure, so new vapor pressure is 195 mm Hg. Okay, calculate the molar mass of the solute. The molar mass of benzene is already 78 gram per mole. Okay, so now if I see here, delta P by P naught is equal to XB, right? So what is delta P value? P naught minus P, P naught minus P, right, by P naught is equal to XB is what? WB, right, by MB. I can write XB is equal to NB by NA, right. So I can write NB is given mass by molar mass and this is WA by MA, right. So we need to calculate this value, right, MB. Okay, now let us substitute all the values. What is the pure pressure? 200, and pressure of the solution is 195. Again this is 200. WB, how much solute is taken? 2 gram, right, and MB is also, MB we have to find out, right, yeah, MB we need to find out. Okay, next, how much gram of solute is taken? WA, 78 gram, and this molar mass is also 78. So now I have to solve this. So I think this is very easy. I'll get 5 by 200 is equal to 2 by MB, or I can write MB is equal to 200 by 5 by 2, right. So you will get around, this is 100, okay, so 20. Okay, so we'll be getting 1 second, did I do any calculation error? We have here 200 mm of Sg, then we have 195, 295, and here okay, the vapor pressure of the benzene is when 2 gram of a non-volatile solute is added to 78 gram of benzene. Benzene has a vapor pressure, given mass by molar mass, given this part is correct. Then okay, so if I reverse this one, I'll get M by 2. Okay, here I think I did a mistake. M by 2, here there is a small error. Okay, 1 second, I'll correct it. So we will get MB by 2 is equal to 200 by 5, right. So MB will be equal to this one 2. So I'll get 5, 4, 40 into 2 is 80. Okay. Next question, again from boiling point. The boiling point of the benzene is 353.23 Kelvin. So we have TB is 353.23. T naught B, okay, boiling point of the pure benzene. When 1.8 gram of a non-volatile, non-ionizable solute was dissolved in 90 gram of benzene, W2 is, sorry, 90 gram of benzene means W1, okay. The boiling point raised to 354.11 Kelvin, okay. So TB is equal to 354.11 Kelvin. Now calculate the molar mass of the solute. Okay, you have to find the molar mass, and the K for benzene, Kb value is 2.53 Kelvin kilogram mole inverse. Okay, so now what we have to calculate? We have to calculate the molar mass of the solute. So delta Tb is equal to Kb into W2 by W1, sorry, W2 by M2 into 1000 by W1. Okay, so what is delta TB value? T naught B minus TB. So 354.11 minus 353.23, okay, equal to Kb value is 2.53, okay. Molality W2 is how much? W2 is 1.8 gram, right? We have not written that. Here I will write down. W2 is 1.8 gram, okay. So 1.8 divided by M2. M2 we have to find out, okay, into 1000 by W1 is 90. Okay, so if I solve this and if you calculate, the M2 value will be 57.27 gram per mole. Okay. Next, question number 7 here. 5.8 gram of a non-volatile solute was dissolved in 100 gram of carbon disulfide. Okay, so W2 is what? 5.8 gram. Carbon sulfide is the solvent, so that means W1 is 100 grams. Okay, molar mass is given, means M1 is also given, that is 76 gram. Okay, the vapor pressure of the solution was found to be 190 mm of Hg. So P is 190 mm Hg. Next, calculate the molecular mass of the solute. Vapor pressure of the pure carbon sulfide, that is P naught, is also 195 mm of Hg. Okay, fine. Next, you have to calculate the molar mass is given, right? So now we'll do the relative lowering vapor pressure formula. P naught minus P by P naught is equal to XB is equal to NB by NA. Okay, so what is P naught value here? 195. Now what is the value of NB and NA, right? So that means NB means I can write N2, that is solute. So that is your 5.8, okay, by M2. And what is N1? Means of the solvent, that is 100 by 76. Okay, so we can calculate here. NB is 5.8, okay, by M2 into Na is 100 by 76. Clear? Now if I solve this M2, if I solve this, M2 value will be around 171.91. You people will be allowed calculator in the examination, so definitely there is no point of any wrong, any mistake in the calculation. The only thing that you should be knowing is the correct formula and its substitution. Okay. Next, last question. This is question number 8 actually. Okay, fine. If 1 gram of non-electrolyte solution is dissolved in 50 gram of benzene, lower the freezing point of the benzene by 0.4 Kelvin. Find the molar mass of the solute. This is also similar question. You will be able to do it now. So W2 is 1 gram. Okay, 50 gram of benzene. W1 is 50 gram of benzene. Okay, lower the freezing point. So delta TF is 0.4 Kelvin. Okay, find the molar mass of the solute. Kf is 5.12 Kelvin kilogram mole inverse. Okay, let us solve this one. Delta TF is equal to Kf into M. So in this, what will happen? Delta TF is equal to Kf into M is W2 by W2 by M2 into 1000 by W1, right? So now if I want to solve this one, what I'll get? Delta TF value is 0.4, okay, Kf value is 5.12, W2 value is 1 gram, M2 value I need to find out, right, into 1000, okay, by W1 is 50 grams. Now you solve this and calculate M2 value and we will get 256 gram per mole. Okay. Next is question number 9 actually. The vapor pressure of pure benzene at a certain temperature is 0.85 bar. So P is 0.85 bar. A non-volatile solute weighing 0.5 gram when added to 39 gram of benzene. So we have W2 is 0.5 gram added to 39 gram of benzene, that is W1, okay, Molar mass is 78, so M1 is 78 gram per mole. Okay. The vapor pressure of the solution then is 0.845 bar. So this is P naught and this is P is 0.845 bar. What is the molecular mass of the solid substance? Again the same formula, relative lowering of vapor pressure, right? P naught minus P by P naught is equal to XB or NB by NA, right? So what is P naught value here? 0.85 minus 0.845 divided by 0.85. Okay. NB. So what is NB here? Number of moles of solute. So that is 0.5 by MB, which we need to calculate, and NA. Okay, number of moles of the solvent. Okay, so here I am writing 2, so that may confuse you. So I'll write A and B here also. So that is WB, WA, NA, right? So Na is what? Given mass by molar mass, so 39 by 78. Okay. So now if I want to calculate here, NB value is 0.5 by MB. Okay. And Na is 39 by 78. Okay. So now if I solve this and calculate MB value, you will be getting around 170 gram per mole. So please check the calculation by your own and tell me whether you are getting the answers or not. Okay. So now coming to the most important topics that you should do from this chapter. So because it is a very high weightage chapter, I want you to do all the chapters, all the questions, but still do not forget to like Henry's law, Raoult's law, colligative properties and Vant Hoff factors. These are the most important topics that you must do from this particular chapter. Okay. And next, if I go for 1 second. Okay. So now if I tell you about the schedule of this particular week, so now we are on Thursday and we did solutions. On Friday there will be vape optics. Saturday you have both maths and bio. So in maths you will be getting applications of integrals, and in bio it is microbes in human welfare. Okay. And Sunday we have only maths, and that is applications of derivatives. Okay. Fine. Next, next one thing. Just a minute. Okay. Okay, so here I want to remind you about the PU2 success blueprint test series. So this is a test series to help you to get 95% or above in your PU board. So in this you will be getting 12 mock tests, which includes 4 part tests and 8 full length papers from the subject PCMB or CS. Okay, apart from the question paper, you will be getting the detailed video solutions with detailed explanation, one-shot revision videos, doubt clarification classes, and the question paper is set according to the latest syllabus and pattern. Okay, so if you want to join this, you can buy this at a discounted price of 599 rupees. So please do not like delay. The link is there in the description section. Please go there, register and buy this test series as soon as possible, because the first test is released on December 15th. Okay, so make sure that you buy this test series before that, so that you can avail all the tests and you can get benefited from this. This will definitely help you to boost your preparation. Okay, fine. So that's all, students, in this video. In the next lecture, next chemistry turn, we'll be doing the next chapter, that is electrochemistry. If you have any doubt in any question, please comment down. You just have to practice all these questions, then definitely this chapter is done for you. Okay, thank you for watching and please subscribe the channel. See you soon in the next class.